In this video, we're going to look at carbonyls and the mechanism for nucleophilic addition, as well as lots of background that you're going to need for A-level chemistry for this topic. So first of all, let's get some terminology right. We have to actually explain what do we mean by a carbonyl compound. So the word carbonyl gets used a lot, but sometimes in slightly different ways. So you need to be careful as to whether you're just talking about a carbonyl group. So there are lots of compounds that contain a C double bond O, including esters, carboxylic acids, and acyl chlorides and amides. However, when we talk about a carbonyl or a carbonyl compound, if you see that in an exam question, for example, it contains a carbonyl, that kind of thing, we usually are just meaning that it is an aldehyde or a ketone. So these are two isomeric functional groups. If you have a look here on the left hand side, we've got propanone, and on the right hand side we've got propanal. So aldehydes and ketones will have the same general formula, and these two are functional group isomers of each other, so they would be C3H6O would be the molecular formula for both of them. So notice that the number of hydrogens is very much like an alkene, and that's because we've got this double bond, which means that we've got 2 less hydrogen in the molecule compared to an alcohol. So that's really useful if you're doing a spectral question and you're like doing some analysis. It gives you a clue that there's a double bond in there. So propanone and propanal have some similarities and some differences. So the similarities is that, of course, they both contain this polar carbon-oxygen double bond. So we've got a dipole there because oxygen is more electronegative than carbon. And then more crucially, the reason that they behave the same and that they do particular reactions that esters and carboxylic acids and acyl chlorides don't do is because attached to that carbon with the double bond O are 2 either carbon groups or hydrogen groups. And one thing I hope you've noticed as you've gone through your organic chemistry mechanisms, all sorts of different reactions, is that it is extremely rare for a carbon-carbon or a carbon-hydrogen bond to break. Okay, we don't lose carbon from molecules unless it's attached to an oxygen. Okay, so we can break sometimes carbon-oxygen bonds, but we do not break carbon-carbon bonds. Okay, and we don't tend to break carbon-hydrogen. Carbon-hydrogen a little bit easier, and this means that aldehydes can be oxidized. So our typical oxidizing agent such as potassium dichromate, but also things like toluenes and also Benedict's solution, all of these are ways for Fehling's test as well. So Fehling's, Benedict's, toluenes are things which only oxidize aldehydes, not alcohols. So they're useful tests. And ketones cannot be oxidized at all, really, unless you're just talking about combustion, because we can't add anything else to that carbon because it would involve breaking carbon-carbon bonds, which we're not generally allowed to do. Okay, so we've got the double bond O. Other than the oxidation of aldehydes, the thing that they've got in common is that they can both undergo nucleophilic addition. So it is nucleophilic because of the positive carbon, which is going to attract a lone pair of electrons from a nucleophile. And it is addition because we have a double bond, which means that we can break that double bond and add across it just like we can with an alkene, but it's not electrophilic because the way that it starts is different. So there are 2 main reactions that involve nucleophilic addition. We've got reduction and we've got addition of HCN. So let's look at reduction. Be really careful because obviously we do loads of redox with inorganic chemistry and we really focus on electrons. But in organic chemistry, oxidation is removing hydrogen or adding oxygen, and reduction means addition of hydrogen, not H plus. Okay, H plus is involved in the mechanism, but if you just add H plus to something, you're not reducing it. Okay, that's just an acid-base reaction. To reduce something, what you're actually going to do is you add H minus and then H plus. So this is what's happening in the mechanism. So we've got a different type of ion here because we need a nucleophile, which is attracted to a carbon. So we can't use H plus to start the reaction because H plus isn't going to be attracted to that delta positive carbon atom. So we need something that's going to provide negative hydrogens. Now, hydrogen doesn't normally take a negative charge when it's bonded to non-metals because it's not electronegative. But if we put hydrogen with metals, or at least things which are very close to being like metals, so things towards the left-hand side, then hydrogen will have the negative oxidation state or form a negative ion. So these are the formulae of our two possible reducing agents. We've got lithium aluminium hydride or lithium aluminium tetrahydride, or much easier simply to write the formula. This is a very strong reducing agent. It is very reactive. It is not covered on all A-level syllabuses. It's such a strong reducing agent which it can also reduces carboxylic acids all the way down to primary alcohols. So this one isn't one that we use as much. So as well as being a strong reducing agent, that means that it's actually super reactive. So if you do learn about lithium aluminium hydride, for example, Edexcel teaches this one, you need to know that the solvent is what we call dry ether. So ether is an organic molecule which we can't use water and we can't use ethanol, another common solvent, with lithium because it will react with it. Also, we can usually just use room temperature. NaBH4 is safer. It's less strong as a reducing agent, so it wouldn't reduce a carboxylic acid. We usually dissolve it in ethanol, but we may use dry ether as well. You can see either. And we're usually going to reflux with sodium borohydride because it is less reactive, so we are going to need a higher temperature to get it to do what we want it to do. In both of these situations, all that this reducing agent is doing is adding the H minus, so adding a nucleophile, which in a moment when we see the mechanism starts the reaction off. After that, we need to add some dilute acid, usually sulfuric acid, and what that's going to do is provide the H plus. So it's like a two-step situation where we add H minus and then we add H plus. Okay, let's have a look at the overall equations. How do we write an equation for reduction? So we're adding hydrogen across the CO double bond, and here are two examples, one with an aldehyde at the top, and then at the bottom we've got a ketone, which is propanone. So with ethanol, we are producing a primary alcohol. So if you look at the product, we have added an H to this carbon, and we've also added an H to the oxygen. So it looks a little bit different because it's drawn differently, but we just added hydrogen across the double bond. The ketone, exactly the same thing has happened, added an H here and here. So this time I've made a secondary alcohol, and it would be impossible to make a tertiary alcohol by this method because a tertiary alcohol can't be made into something that has a double bond, right? Cannot be oxidized. If you remember with oxidation that we use O in brackets, again, it's very complicated to write the half equations involving, say, NaBH4. So we use H in brackets. So it's not H2. If I wrote H2, the equation would be balanced. But hydrogen gas, H2, isn't the reagent. It's LiAlH4 or NaBH4. So what we do is this just represents the reducing agent, and we have the 2 in front because I need 2 hydrogens. I also want to look at what this would look like for structural formulae, because sometimes people can get a little bit thrown. There's a few little errors we can make. So if you have to write an equation, you can write displayed formulae. It's not an issue if that's what you need to do, but be used to recognizing what the structure looks like. So for an aldehyde, my structural formula would look like that: CH3CHO, not OH. Okay, if OH means alcohol, HO means aldehyde. I'm then going to add my 2 H's. There's no plus on there. Be careful, because we're so used to putting a plus, especially if you're doing the acids topic and you're thinking about concentration of hydrogen ions. And then, of course, ethanol is a very easy structural formula. With my ketone, I'm going to write CH3, then just CO, and then CH3. 2 lots of H. Even I started doing it then. I was about to put a plus on there. It's so easy to do. And then CH3, CHOH, brackets if you want, not necessary, or you could stick it above. What I don't want to see happening is just this whole thing, C3H7OH, or in any way where you start writing molecular formula. So if you know, for example, that this is producing propan-2-ol, and we're starting with propanone, just be clear about the product. Make sure that it's not ambiguous. Make sure that it couldn't be a different alcohol. So it's not such a problem here with ethanol. I could write C2H5OH, but that's because there's no other place I could put the OH. There's only 2 carbons there. The minute there's a choice, you need to show it in your structural formula. So let's have a look at the mechanism for reduction. It's a really simple mechanism. As I said, we're adding H minus, and then we're adding H plus. So the H minus comes from the reducing agent. So it could be like attached to an Al or a B. So this is what the actual ion would look like. It would have a shape, obviously, but I haven't drawn a shape. This whole thing would have a minus charge. However, I've not really seen that used in A level, and most of the time they're just going to simplify it with just H minus. It's a nucleophile, so we need to put in a lone pair. And for any nucleophilic reaction, well, for pretty much all reactions except benzene, mechanisms need to show a dipole at the start, because what we're doing is explaining why the electrons go to a particular place and why a bond breaks. So the electrons go to the carbon because it's delta positive, and then the bond breaks. But it's a double bond that breaks. So unlike mechanisms that you might have seen before, where a nucleophile goes in and you have, for example, a bromine, in this situation we would completely break off, and that's where we have nucleophilic substitution, because it's a single bond that we're breaking. But because it's addition, we are actually only breaking a double bond, and we're going to still have the carbon and oxygen attached. Just a little point on arrows. So I want you to notice that this starts in the lone pair. You don't have to put the lone pair next to the negative charge, but you do need to have your arrow starting on the lone pair. Don't have it on the other side. It has to go directly to this carbon. And then this arrow needs to start really neatly in the middle of that double bond. Don't have it too close to the carbon or too close to the oxygen. Next thing then that we need to draw is the intermediate part of this reaction. So I'm just going to draw that as CH3 because nothing's happening to that group. There is my carbon still attached to my oxygen. Hydrogen is still attached, and the new hydrogen is attached as well. So this carbon doesn't have a charge, it's got 4 bonds around it, but the oxygen just accepted that pair of electrons from the double bond, and so it now has a negative charge. And what did we say? We said we're going to add H plus afterwards, arrow from lone pair to H plus, which just comes from the acid. Alternatively, just in case you are given something that looks slightly different, the H+, I mean, this is going to make an alcohol. Alcohols are very stable compounds at the end of the day. So if there's no acid around, it is just as likely that this oxygen would take hydrogen from water. If you do that, you're going to need 2 arrows. So this is a delta plus, delta minus. The lone pair goes to the hydrogen, is forming a bond, which means we need to break this bond. So it would leave behind a hydroxide ion. So it may well be that you see that in a mechanism. Notice it's just doing the same thing. It's still taking H+, but it's taking it from a water molecule and leaving behind an OH-. But usually we add acid at the end of this mechanism. I've seen recent exam questions that ask to explain why we do that. The word that's happening to here, where we take an O- and we add H+, H+ is called a proton. So you can simply say, this is a genuine chemistry verb, that we are protonating the O-. Don't call it oxide because oxide is like O2- on its own, and this is joined to something, but just call it the O-. So protonate is a good word to use when we are adding H+ to something. You can also deprotonate things, which is what happens to acids. So that is our reduction, addition of hydrogen to make primary, secondary alcohols. Now we are going to look at our addition of HCN. So HCN is called hydrogen cyanide, and the use of this is to extend the carbon chain. I said addition of cyanide here, not just HCN. That's because you can also substitute Cn- as an ion in itself. So hydrogen cyanide, I'm just going to do a little dot and cross diagram, has a single bond, 1, 2, 3, 4, oops, between the carbon and the hydrogen, and a triple bond between the carbon and nitrogen. And that's a covalent molecule, therefore, which we could also write as this. And then it's actually a weak acid, so it splits up into H+ and Cn-. So in the previous, remember that we had H- and then we added H+. In the addition of HCN, we're just going to add Cn- first to the carbon, and then we are going to add H+ afterwards onto the oxygen. So this ion is called the cyanide ion. There's a little bit of confusion in the naming of this topic. So the next thing is, what is the product called? So if I have a C double bond O, I'm just going to give that a CH3 and an H. So when I add HCN, excuse the messy drawings, then that is a C, that is a C. We're going to add a Cn, and then the O is going to add an H. So it's addition, so there's only one product. And it's got 2 functional groups. So it's got the Cn part, oops, drawn all over it, and it's got the OH part. So OH is an alcohol. It is an alcohol, but because it also contains a nitrile. So I want you to realize that cyanide is just the name for the ion, or for when it's just attached to something like potassium or sodium or hydrogen. As soon as it's attached to a carbon, it becomes the name of a functional group and it becomes a nitrile. This is not different to stuff you've seen before, right? Because OH- is called hydroxide. And then when it's attached to a carbon, it's called an alcohol. So you have seen this before. It's not as scary as you think. So this is now called a nitrile, but because it contains an OH group, we're going to need to mention that, but we can't call it ol because nitrile goes into the name. We'll name some of the products when we look at the mechanism, so you get an example of that. Also mention, of course, now that this starts as ethanol, 2 carbons, and it ends as, let's name it actually, 2-hydroxy propane nitrile. Gonna go on the edge. because it has 3 carbons. So the carbon with the double bond O now becomes carbon number 2 because I've just added another carbon onto it. So actually, when we are carrying out this reaction, we don't use HCN. HCN, hydrogen cyanide, is in fact a toxic gas. Neither of those things are ideal, okay? So if it's a gas, I can't really contain it very well, and it being toxic, extremely toxic. And also HCN is no good because I don't want the molecule. What I want, in the same way as the previous reactions, I didn't want H2. I wanted H minus followed by H plus. What I want is Cn minus and then H plus. So what we do is we use something like NaCN or KCN. Now those are ionic compounds like NaCl or NaOH. When we dissolve them, they're going to split into ions, separate ions, which means I'm going to have a nice high concentration of my cyanide ion in solution because they're very soluble salts. I can dissolve hydrogen cyanide, but when I do, because it's a weak acid, only partly dissociates, so I'd have a very low concentration of Cn minus. I also need the H plus though, so I'm just going to add some sulfuric acid. The reason that we tend not to add hydrochloric acid is because chloride ions are nucleophiles themselves and we don't want to get those involved. So in terms of the balanced equation, you can see with the ethanol, I'm just adding HCN. Cn adds onto the carbon and the H adds onto the oxygen. So let's take a look at the mechanism for a couple of different molecules for the addition of HCN. So like the addition of hydrogen, like the reduction, it's going to be a 2-part where we add the negative ion first, the cyanide ion, and then we add H+. So when you're drawing a cyanide ion, it's got a negative charge. Because it's going to be a nucleophile, we're going to put a lone pair on it. Now, let's just go back to that drawing of hydrogen cyanide that we drew. So this is the molecule where we have a triple bond. So we could also draw a displayed formula. Now, this bond is going to break and H is going to come off as H+. It's going to leave the electron behind. So what that means is when I see the cyanide ion, what you can see is that there's a lone pair on both sides. So there's a lone pair on the nitrogen and the carbon. But the carbon is the thing that has the negative charge because here is the electron that is not belonging to the carbon. That was the hydrogen ion's electron. So the negative charge is on the carbon. That's the pair of electrons that is going to be donated. And it's not nitrogen. So often nitrogen does have a lone pair, well, it does always have a lone pair, almost always, and it is involved in some mechanisms, but not in this one. If you're doing a nucleophilic reaction, we should always have our dipole, because that's the whole reason the cyanide ion is going in for attack. You can put the negative charge here on the other side in the same way that we might do that for hydroxide. So, we could often draw that. But I think it's very good practice to always try and put the charge on the correct atom because there's going to be other mechanisms like ones you haven't seen before or maybe just ones you forgot where you need to know where the charge goes. Don't just always default to sticking it at the end. Double bond opens up. So we get our intermediate. I'm just going to write CH3 here. This now becomes a negative charge. This becomes a H and this becomes a Cn. Often get students asking me like, when do we draw the lone pairs? Because there's more lone pairs in this molecule at the start than I've drawn. There's a lone pair on this nitrogen that I haven't put in, and there's 2 lone pairs on an oxygen. So the reason I haven't drawn them is because they are not doing anything in the mechanism. So we only put them in because we're going to make a bond with them. So either an arrow needs to start in a bond or on a lone pair, because we're moving a pair of electrons. So if I'm not using those lone pairs for anything, I don't need to draw all of them in. And then now, therefore, because I am about to bond this oxygen to this hydrogen ion, then I will draw one of the 3 lone pairs that that oxygen atom actually has, because it's only sharing one of its electrons. Okay, here's my product. And these could be drawn in any kind of order. It doesn't really matter, as long as everything's joined in the correct order. It doesn't really matter, as in I could put my CN where my H is and so on. If we had a ketone, all extremely similar, just to show you how very samey this mechanism is. You need to be careful on the position of those arrows, as we have said. Make sure they go from the middle of the bond and not like one of the atoms. And there is my H+. So in other mechanisms, you may have done about the double bond in the oxygen reforming. That only happens if we've got a bond that we can break, but all of these are CC bonds, so we're not going to break any of those. And therefore, I'm going to make this product, which is COH, CN. Remember that that is a triple bond. So if I was asked for a displayed formula, I'm going to show that right now, actually. In case it said draw the displayed formula of the product. Obviously, I think we're probably all pretty good at putting in all the H's, although I have seen a lot of people accidentally just put one CH3. Don't forget that OH has a bond, and don't forget that the CN group has a triple bond. You don't actually, in fact, I don't know why I did it at that angle, because this is 180 degrees. There we go. So make sure that you've shown every single bond if you are doing displayed. Let's just talk about the naming of these products. So we've started on this side with ethanal at the top. We've added a carbon on. So this is my nitrile. That's the main functional group. There's 3 carbons in that chain. So it's propane nitrile. Notice the E is there. It's not there in ethanal or ethanoic acid or ethanol because they have vowels coming after the N. But because this has an N afterwards, we keep the E there. That's the rule about whether we take the E away or whether we leave it. And then there is this group here. Now, by default, because the nitrile part, the CN, has to be at the end of the chain, that has to be carbon number 1. That's the rules. So this means that we work backwards, and this is carbon number 2. And actually, this type of reaction is pretty much always going to make a 2-hydroxy propane nitrile or whatever, because if you think about it, the OH group is always going to be on the same carbon that we've attached the CN to, and that's now going to become carbon number 2. At the bottom, we've got propanone, but you need to be careful about the naming because actually we've added the CN in the middle and not at the end, so it doesn't just become butane nitrile. We don't just add another carbon onto the name. This is carbon number 1 again, so the CN carbon. This is carbon number 2, and can you see I can go either left or right, and it's exactly the same. So for sake of argument, I'll go to the right, and this is carbon number 3. So that is my main chain. So it's still propane nitrile. And then as well as the hydroxy group on carbon number 2, there is also a methyl group. So I'm going to call it 2-hydroxy, not hydroxyl. Okay, there's no L in that. I don't know why. And then there is 2-methyl. Why are they that way around? Just simply alphabet at this point. So if you've got more than one group on a carbon, like a hydroxy and a methyl, or a chlorine and a methyl, we're going to put them in alphabetical order. Okay, just want to now talk about optical isomerism. This comes up a lot with AQA and could also a lot with Edexcel, little bit with OCR. So if we look at this example again with ethanal and the addition of HCN, what you can see is that this carbon here has got 4 different groups attached. So this carbon is chiral, which means that actually, although we've drawn this flat, that is a tetrahedral structure, and actually it has optical isomers. So we've got our mirror in between, and we can see that these are non-superimposable mirror images, which is our definition of what optical isomers are. So they're not the same molecule. The reason they're called optical is because of the effect that they have on plain polarized light. They rotate it, and they rotate it in opposite directions by the same amount. Now, the reason that I'm relating this to the mechanism is because when we start the reaction with our aldehyde, this is a trigonal planar shape. So there's 3 bonds, 3 areas of electrons around that carbon. We've got the double bond, but that can't spread out. So we have a 120-degree angle, and this is completely flat. So the Cn-, the cyanide ion here, could attack that carbon from the top or from the bottom. So it can go above or below. And if you imagine like an umbrella kind of unfolding or flipping round, when it attacks from above, then these 3 groups will push away in a particular direction away from it because it's electron repulsion. So then we'll get our tetrahedral shape. And if it comes from the opposite side, the tetrahedral shape will still happen, but it will be the opposite optical isomer. So there is a 50-50 chance of both isomers forming, which means that at the end of the reaction, you won't get one optical isomer, you will get an equal mix of both of them, which means that actually it won't have any effect on light. If I try to shine the plain polarized light through it to test, it will go straight through. That's what we call a racemic mixture. So although we have this option of stereoisomerism, we're going to make both of them in equal amounts. And this can be an issue for like drug manufacture where you only want one isomer. Alternatively, just be careful and don't leap to any conclusions, because it's very common in a multiple choice question, you know, when you're trying to decide which ones are true out of a load of statements. You don't always get optical isomers from this addition reaction. For aldehydes, you always will, because for aldehydes, you've got H, CN, OH, and then your carbon chain. But if we took for our propanone example, look at the end product and see that it's not chiral, because that carbon has actually got 2 methyl groups attached to it. So they're the same, it hasn't got 4 different groups. So if you have a symmetrical ketone, then your product will not be chiral. Finally, let's just look at what the hell we're going to do with this nitrile group, because actually nitriles aren't that great. They're not really common as functional groups that we might find. So it's much more likely if we're doing a synthetic group and we're trying to make something, that we're actually trying to make a different functional group. So we use the nitrile to make the carbon chain 1 carbon longer. That's really helpful. But actually the CN group is not that useful. So we can do 2 things, either reduction or hydrolysis. And we're going to make 2 different things. So let's keep it simple. I'm going to say we're going to go to our propane nitrile, 2-hydroxypropane nitrile. So reduction, we've already covered reduction. It means addition of hydrogen in terms of organic chemistry. We're reducing this part though, so we're adding across. Remember that that is a triple bond. So let's draw that out actually, so that we can see clearly how it changes. So think about how we add to an alkene. How we add to an alkene is we had a hydrogen and hydrogen gas, and then what we end up with is we break the double bond and we end up with an H added across. Okay, how is this similar and how is this different? Well, reduction of nitriles, we still use hydrogen, H2. We use a catalyst, nickel, which we also can use with alkenes, although sometimes we might use platinum. So we've got nickel, we've got hydrogen. In terms of amount of hydrogen, I'm going to need 2 H2s, and that's because I've got a triple bond. So it's not enough just to add 2 hydrogen atoms, because that will only break the first part of it. I actually have to add 4 hydrogen atoms in total. So my methyl group stays the same, this stays the same, this stays the same, and then this now has 2 hydrogens on it. And the nitrogen now has 2 hydrogens on it as well. And that means my nitrogen's got the right number of bonds. So that's my amine. This has got 4 carbons in it. So, oh, it hasn't, it's got 3. So this would be propylamine. And then we've got an OH group. I wouldn't worry too much about naming that one. It's more likely that you're going to have to actually work on how you get to it. Then the other reaction is hydrolysis, and we tend to only use hydrolysis more commonly when we're talking about esters and perhaps amides, and of course in biology when we're talking about hydrolysis of polypeptides or hydrolysis of long molecules like starch. Hydrolysis is just breaking bonds with water. So I'm breaking this bond. Adding water across it is what's going to help me to break it. Just like how I needed 2 hydrogens because it was a triple bond, I'm actually going to need to add 2 lots of water as well. And just like with esters and amides, I can't break this bond just by adding water. It needs to be something else a bit more to it. So we would usually use acid. So I'm going to say plus HCl. So let's look at what happens. I've got lots of hydrogen, 4 hydrogens and 2 oxygens in my water. Thinking about which way they would go. Well, my hydrogen, my carbon is delta plus and nitrogen is delta minus because nitrogen is more electronegative. So the oxygen's going to tend to want to be bonding to the carbon. It's going to be attracted to that. And the hydrogen is going to be more attracted to the nitrogen. So I'm going to end up with a carboxylic acid. Now that's used 2 oxygens and 1 hydrogen, leaving me with 3 hydrogens left, which means that I could, in theory, make NH3. However, it doesn't work if I only add water. I've got HCl, so NH3 and HCl will react together to make ammonium chloride. And you can put the charges on if you want, or you could simply write it in a balanced equation as NH4Cl.